Now there is a law of length which is called as R directly proportional to L. That is, resistance is directly proportional to length of a conductor and it is inversely proportional to the cross-sectional area of the conductor. So combining these two equations, we are going to get R is directly proportional to L by A. Now, as we have discussed many times, if you remove a proportionality symbol, you must insert an equality symbol along with a constant. So R is equal to rho L by A, where rho is the constant of proportionality called as resistivity or specific resistance. Here note the difference. Capital R is resistance, rho is resistivity or specific resistance. This is a constant. Given the temperature is constant, this is a constant for a same type of material. If you calculate the resistivity of wood at a certain temperature, it will be same to the same. If you make different materials from the same wood, you are going to get same amount of resistivity, but resistance will be different depending on their length and area. Resistivity is a constant at a given temperature. Now, if from this equation, if we simplify further, we will get to rho is equal to R into A by L. So the unit, SI unit of resistivity will be SI unit of resistance into SI unit of area by SI unit of length. So that implies SI unit of resistivity will be ohm into area's unit is meter square by length's unit is meter. So meter and meter square will cancel. So SI unit of resistivity is ohm into meter. Ohm meter. Alright. Now let us find the dimensional formula of resistivity. Since resistivity is equal to R into A by L, dimension of resistivity will be equal to dimension of resistance into dimension of area by dimension of length, which on simplifying you are going to get M1 L3 T minus 3 A minus 2. Now since resistivity only depends on the temperature, it does not depend on the cross section of the conductors. If you take a copper wire, thick copper wire at some temperature, say 25 degrees Celsius, and if you take a thin copper wire at same temperature, that is 25 degrees Celsius, their resistance might not be same, but their resistivity or specific resistance has to be same, will be same, because they are made up of the same material, that is copper. Now we have also discussed about this formula, that is R is equal to ml by n q square a tau. Now from the numerator, if we take L outside, and from the denominator if we take A outside, then we are going to get R is equal to m by n q square tau into L by A. But from here we had a equation, that is R is equal to rho L by A. So we also know that R is equal to rho L by A. If we compare these two equations, we will get rho is equal to m by n q square tau. So out of here, m, that is the mass of the free electron, is a constant, and q, that is charge of free electron, is a constant. What was n? N was the number density of free electrons. It is not a constant because it depends on the material you are taking. For example, if you take a conductor, it will have a high N. Its number of free electrons will be high. If you take an insulator like plastic or wood, the value of N will be less. And tau is the relaxation time. That is the time between two successive collisions. Now we can say that as m and q are constants, rho is directly proportional to 1 by n. that is rho is inversely proportional to n, and rho is also inversely proportional to tau. So if you are going to use a material whose number of free electrons are more, its resistivity will be less. And if the relaxation time is larger, the resistivity of that material will be less. Now, how will the relaxation time be larger? If the molecules are moving slowly, then they will relax for a larger amount of time. Or we can say if the free electrons are moving slowly, they will have a higher relaxation time. When will the free electrons move slowly? The free electrons will move slowly if temperature is less. So if temperature is less, relaxation time will increase and resistivity will decrease. So try to understand, if temperature decreases, relaxation time increases, resistivity decreases. So we can indirectly connect resistivity with temperature, that is, if temperature decreases, resistivity decreases. So we can say resistivity is directly proportional to temperature. That is, if temperature will increase, resistivity will increase. If temperature will decrease, resistivity will decrease, and so on. Now let us see. This is just now the sentence that we discussed. This was only for a conductor. But now let us see for some different materials how resistivity changes with temperature. For this we have to remember an equation, that is rho is equal to rho naught 1 plus alpha bar delta T. Rho naught is the initial resistivity at the absolute temperature. Now the value of alpha bar is different for different materials. It is a constant which is called as the coefficient of resistivity, temperature coefficient of resistivity, and depending on the type of alpha bar value, the variation of resistivity with temperature can be read. For example, if alpha bar is positive, then if you increase delta T, rho is going to increase. If alpha bar is negative, if you are going to increase delta T, rho will decrease. So for conductors, alpha bar is positive. That is, if you increase temperature, resistivity is going to increase as well. But for insulators and semiconductors, the alpha bar is negative, which brings out inverse proportion between resistivity and temperature for insulators as well as semiconductors. So you can see in these two type of materials, if you increase temperature, the graph of resistivity keeps on falling down. Now resistivity and resistance are nearly related to each other. So if resistivity increases with temperature for conductors, resistance also follows the same pattern. Resistance also has an equation, something nearly similar to that of resistivity's equation. It is R dash is equal to R naught 1 plus alpha delta T, and alpha is positive for conductors, but it is negative for insulators and semiconductors. So R is directly proportional to temperature for conductors, but it is inversely proportional to temperature for semiconductors and insulators. Exactly same as resistivity. So if you remember about resistivity, you are easily going to be able to remember about resistance. Alright.